Right, this is worksheet 15.2, double integrals over general regions. Let's go ahead and get started with number one. We want to compute this iterated integral. Whenever we're doing a double integral over a general region, for these types of regions, the order of integration is especially important because the shape of the region can influence how easy the integral is, like very drastically. So we always want to ask ourselves first, do I want to use this order of integration or do I want to change it? If I use this order of integration, I'm going to have to integrate sine of y dy, which is fine, that's not hard. And then I'm going to have to integrate x dx, which, depending on what the earlier integral is, maybe will be hard. And so we can try to swap the order, because I'm realizing when we integrate the sine, we'll have a cosine of x term, and then we'd have to do integration by parts. Whereas if we integrated with respect to x first, actually I think we would probably still have an integration by parts. Okay, so I don't think the order of integration is going to change this problem too much, so let's just integrate it directly. This is integral from 0 to pi, and then integral of sine of y is negative cosine of y, and then y is going to go from 0 to x dx. And so let's see, this is negative integral from 0 to pi of x cosine of x, and then cosine of 0 is 1, so minus x. Okay, so now we need to integrate x cosine of x. I'm going to use integration by parts. So we'll differentiate x and integrate cosine of x, because if we differentiate x, it'll go away after a certain number of terms. So we get that. Integral cosine of x is negative sine of x. Integral of negative sine of x is negative cosine of x. So this is equal to negative x sine of x plus cosine of x. And then integral of x is 1/2 x squared from 0 to pi. Okay, so let's see. When x is 0, when x is pi, sine of pi is 0, so that one goes away. Cosine of pi is negative 1 minus 1/2 pi squared. When x is 0, x sine of x is 0. Cosine of x is 1, so I'll subtract 1. And that last term is 0. So this is equal to 2 plus 1/2 pi squared. Okay, that one wasn't too bad, just some integration by parts, but otherwise direct integral. Okay, number 2. We want to decide without calculation if each of these integrals are positive, negative, or 0. And D is the unit circle centered at the origin. Okay, so part A, the integral over the bottom half of that circle of y cubed plus y to the 5th. Okay, in the bottom half we're in this region, and so what we want to ask ourselves is, when we're in that region, is y cubed positive or negative, and is y to the 5th positive or negative? If we're in this bottom half, y is always negative, and so y cubed and y to the 5th are always negative, and if we integrate a negative function, we're going to get something negative. So that one's going to be negative. For part B, we're in the top half. In the top half of this circle, y is always positive, so y cubed and y to the 5th are always positive. So when we integrate them, we'll get something positive. When we integrate over the entire circle, we're just adding a and b together, because that's the same thing as integrating over the bottom half, integrating over the top half, and then adding those two together. But a and b had the opposite sign, and you may be wondering, how do we know that they're going to exactly cancel out? Because I'm going to argue that there's 0, that this is 0. And you may ask, okay, how do you know that the top and the bottom are going to cancel each other out? The reason is that this circle is symmetric about the x-axis. And so whenever I have a point here that was, I think the top was positive, so I'll call this positive, I don't know, y0. There will be another term on the mirror of the circle that is just the negative value. And when we end up integrating over all of the the points in the circle, because that's what we're really doing. We're doing a double integral. We're integrating over all the points in the circle. Then these two will cancel out because they have the opposite sign. These two will cancel out because they have the opposite sign. These two will cancel out because they have the opposite sign. And these two will cancel out because they have the opposite sign. And so because the circle is symmetric, this integral is going to be 0. Sort of just a visual argument for why that's true. Okay. Part D, we're integrating over the left half. Similarly, over the left half, we see that we always have these guys canceling out on the left half. So this will also be 0. And the same thing for the right half. We'll always have these pairs of points canceling out. And so the right half is also 0. The reason they didn't cancel out on the bottom or top is because there was nothing for this purple point to cancel out with. Because this red point is also positive. And so those two aren't going to cancel out, they're going to add together. So that's why they didn't cancel out on the top or bottom, but they did cancel out on the other 3. Okay. Number 3, we want to write an iterated integral for this integral using vertical and horizontal cross sections. Okay, part A. Bounded by y equal to e to the negative x, which looks something like this. Y equals 1, which looks something like this. And x equals ln3, which looks something like this. So we're going to be using this region. I always like to say you should probably start by finding the vertices of your region. So let's see. This bottom right one is going to be where e to the negative x intersects with the curve x equals ln3. And so if we plug x equals ln3 into that equation, we'll get y equals e to the negative ln of 3, which is equal to 1/3. Or I'll show one extra step. This is e to the ln of 1/3, because we can bring that negative inside. We get 1/3. And so that point is not 1/3. Ln of 3 and 1/3. Similarly, this point is the intersection between x equals ln of 3 and y equals 1, so that's easy. It's just ln of 3 and 1. And then that one is the intersection of y equals 1 and y equals e to the negative x. So if we want to find the x coordinate, we do this, and it gives us x equals 0. So that coordinate is 0, 1. Okay, so now we can set up our integrals. First, we'll do, I don't know which one's vertical and horizontal off the top of my brain, so I'm going to just do integral with respect to x first. So if we integrate with respect to x, the minimum value for x is right here, and the minimum value is 0. The maximum value for x is right here, and that maximum value is ln of 3. Okay, and then we do the same thing for y, except this time we have to think about cross sections instead of just minimum and maximum values. So pink is my cross section color. And what we want to think about is for any given value of x, what two curves are those cross sections between? So this lower curve that they're on is definitely my e to the negative x. So be integral from e to the negative x. And the upper curve is definitely 1. So that's y equals 1. My integrand is just 1. And then dA, we have dy dx. So that's vertical cross sections. Now for horizontal, instead of doing x first, we want to do y first. So let's see, the minimum value for y in this region, and I'll use red now for my horizontal cross sections. The minimum value for y is at this point right here, where y is equal to 1/3. So the bottom integral is going to be 1/3. And then the maximum value for y is going to be right here, where it's equal to 1. Okay, now we have to find our x integral, and to do that we're going to say, okay, if y is a constant, that's these horizontal cross sections, what two curves our cross section is going to be between. And here we can see that the leftmost curve is this one, the y equals e to the negative x. And if y is equal to e to the negative x, then negative x is equal to ln of y, so x is equal to ln of 1 over y. And on the rightmost curve, we're right here. And on that one, x is just equal to ln of 3. dx dy. Okay. And that is it. That is that problem. Well, I guess we have to do part B now. So this one is going to be a similar thought process, but this time we have x squared and x plus 2. So that and x plus 2 is going to be like here-ish. So let's see, we still need to find these intersection points. To find those intersection points, we'd have to find when the two curves are equal. One of the solutions is going to be 2, 2, and the other one is going to be negative 1, 1. I can just sort of see that by looking at it, but if you can't see that, then you can solve this by factoring it or using the quadratic formula. And so our region is going to be right here in blue. And we want to find that region again using the vertical and horizontal cross sections. So first we'll do the x integral first. The minimum value for x in this region is negative 1. The maximum value is 2 because of here and here. Those are the minimum maximum values of x. And then for each value of x, if x is being held constant, so we have a vertical cross section, y is always bounded between those two curves. The upper one, which is x plus 2, and the lower one, which is just x squared. So the lower one we said is x squared, the upper one is x plus 2. So that is vertical. For horizontal, we are once again going to start with y. So let's see, the minimum value for y in this region is 0 right here, and the maximum value is 2 up here. So this is going to be an integral from 0 to 2. And now we're going to draw our horizontal cross section, because those are where y is constant. And now we'll ask ourselves, okay, along each of those lines, what are the two curves that bound y? And the answer is, well, it depends. If we are below, I'll use this in purple. If we're below this line, which is y equals 1, because it's where we intersect this point, then the two curves are both this x squared curve. If we're above that line, then it's between these two curves. And so because of that, we need to split up the integral into below that line and above that line. Okay? Once we've done that, if we're below that line, then we're between the two x squared curves. So if we solve for x, we get x is equal to plus or minus root y. And so the bottom one is going to be negative root y, and the top one is going to be positive root y. And then if we're in the upper region, the left curve is going to be x plus 2. And so x is going to be y minus 2. And the upper curve, again, is going to be root y, because that is the right side of this parabola, is root y. Okay, so that's that problem. I do think this is an important one to know how to do. You will maybe be asked to do this on an exam, and then even if not, you need to know how to set up bounds of integrals on an exam. Okay, number 4, we want to sketch the region of integration, reverse the order, and evaluate the integral. The reason we really do need to do this is cosine of x squared does not have an integral. You can't integrate that no matter how hard you try. And so we do actually need to sketch the region of integration. So let's see. we start with y, and y can be anywhere between 0 and root pi. Okay, and then we do x. For any given value of y, so those are going to be y cross sections I do in red. It's going to be here. The maximum value is going to be root pi. So I'm always going to end here at root pi. And the minimum value is going to be y. So I can draw the curve x equals y, which is this curve here. And the minimum value of these cross sections is going to be there. And so these are my cross sections, and my region is going to look like this, right here. Hopefully that made sense how I set that up. Because now, if we want to convert the other way, I'll ask myself, okay, the minimum value of x in this region is 0. The maximum is root pi. So this x is still going to be 0 to root pi. But now, if I draw my vertical cross sections, because I'm holding x constant, the minimum value of y is always 0, because it always hits this x-axis. And the maximum value is always x, because it's on the line y equals x. Okay, and so now my integrand is still cosine of x squared. I would do dy dx. And we can see why this procedure is so useful now, because we can integrate this very easily now, because we're integrating with respect to y and not x. So that'll just be integral from 0 to root pi of x cosine of x squared dx. I'm just skipping the step there where I plug in the top and bottom. Okay, and now we can do this with just a u sub. So let's say u is equal to x squared, du is equal to 2x dx, so then 1/2 du is x dx. And then we get that this is equal to the integral, okay, when x is 0, u is 0. When x is root pi, u is pi. And then this is 1/2 cosine of u du, which is 1/2 times sine of pi minus sine of 0, which is just equal to 0. Great, okay. Hopefully that one makes sense. Let's move on to number 5. Again, we want to sketch the region of integration and evaluate the integral. Okay, so it tells us that R is enclosed between x equals 0, which is changed to purple, I think. So let's see, if this is x, this is y, then x is equal to 0 here. And x is equal to root 1 minus y squared. Okay, since x is a square root of something, it's always positive, and I know that this is a circle of radius 1. So it's that curve, and we are in this region here. Okay, and so we might want to ask ourselves, do I want to integrate with respect to x or y first? Here I think it'll be best to integrate with respect to y first, because then my cross sections look like this, which are pretty simple cross sections. So let's do this. Y goes from 0 to 1, or sorry, negative 1 to 1, because the minimum value of y is down here at negative 1, and the maximum value is up here at 1. And then on each of these cross sections, the minimum value for x is 0, and the maximum value is up here, which is root 1 minus y squared. And then we have x times y squared dx dy. Okay, so now we treat y as a constant because we're only doing the innermost integral. This will be 1/2 integral from negative 1 to 1 of x squared y squared, with x going from 0 to root 1 minus y squared. So then we just plug those in. We get 1/2 integral from negative 1 to 1 of 1 minus y squared times y squared dy, which is 1/2 integral from -1 to 1 of y squared minus y to the 4th dy. I'm going to use the fact that that integrand is even to multiply by a factor of 2. And then this is equal to 1/3 minus 1/5, which I'm just doing that in my head because I think you guys can do that part, which is what, 2/15, I think? No. Let me write that. That's 5/15 minus 3/15. Yeah, 2/15. Okay, that's my final answer. All right, now we can do number 6. My computer's at low battery. Okay. I will charge it after this. So we need to find the volume of the solid bounded by the cylinder y squared plus z squared equals 4, and these planes in the first octant. Okay, this is going to stretch my drawing ability. So I'm going to start by drawing the region of the xy plane. That's always a good starting strategy. I'm going to draw the line y is equal to 1/2 x, which is this line here. I also want the cylinder. Here, I'm going to draw the curves in purple. Purple. Okay. So we have that one. We have x equals 0, which is this. We have the cylinder y squared plus z squared. Oh my god. Why? This is so ugly. Okay, I'm going to put this in Desmos 3D just so I have an easier time visualizing what I'm thinking. We have, let's get rid of all you guys from the last worksheet. Okay, so we have y squared plus z squared is equal to 4, which is that cylinder right there. We have x is equal to 2y. Which is that plane right there. We have x is equal to 0 and z is equal to 0. Okay, and so the region that we want is bounded between those 4 graphs. And actually there's, oh, this is really ugly because there's 2. Oh, I need to plug in my computer. Oh no, I can do this. Okay, I can do this for a bit without. So yeah, this is ugly because there are actually 2 such regions. There's this one right here. Oh, stop, I'm not doing that. Stop. This one right here that I'm looking at on this side. That's between the green, blue, red, and purple. And then on the flip side, we have this region, which is exactly the same, but it is also a region we have to worry about. Okay, so I'm going to sort of do this graphically. The predominant strategy for these is look at these from like sort of the bird's eye view, so that we're just sort of getting the XY plane picture. When we do that, we see, that our region is between, and I'll just draw this back over here. So I did draw these. We have this region right here is the one that we want for our graph. And then we know that the height of the function is between the plane, the purple plane on the bottom, and the red curve on the top. So the height of the function is it's the z coordinate of this guy, so that's root 4 minus y squared. Okay, and so now we need to set up the integral over this region up to this height, and then we need to multiply by 2 because there are 2 such regions, one sort of here in the top right and one in the bottom left. The reason the top left and the bottom right don't count is because they're not bounded because they go on forever. And so those won't count. Okay. And so then the volume is equal to 2 times the integral. Let's see. I'm going to do... Oh, what? Stop. Okay. I'm going to do with respect to y first because that goes through the y-axis. So the minimum value for y is 0. The maximum value for y is when oh no. So you can see that this cylinder is a cylinder of, what's the radius? 2. And so the maximum value for y is when we've gone 2 units upward. You can sort of see this on the graph here. This value, I don't think OBS captures my cursor, but I think I can put the point 0 to 0. It's gray right now, so it's not very easy to see, but I can make it like orange. So you can see this orange point I put right there. That's where the cylinder intersects with my purple plane, and so that's going to be my maximum value for y. So maximum value for y is 2. Okay. And so now I have to do the x integral. So that x integral will be from 0 to this purple line right here, which is just 2y. And then we have to integrate the height, which is root 4 minus y squared. That looks like a 4. What? Why did you delete those two? I really need to plug in my computer or it's going to keep doing stuff like this. 4 minus y squared dx dy. Okay. Fortunately, the dx integral is very easy. This is 2 times the integral from 0 to 2 of 2y times the square root of 4 minus y squared dy. And now we can just do a u sub. So u is equal to 4 minus y squared. Du is equal to... this computer really needs to be plugged in. Negative 2y dy. So then negative du is equal to 2y dy. And so this is equal to 2 times the integral, or I should say negative 2 times the integral from, okay, let's see, when y is 0, u is 4. When y is 2, u is 0. And then we have the 2y, so this is just root u du. I'll use that negative sign to change the order of integration. And I'll write this as u to the 1/2. Okay, now we just use the power rule. So this will be 4/3 u to the 3/2 from 0 to 4, which is, let's see, 4/3. That's not, what's wrong with you? This computer needs to be plugged in. 4/3 times, okay, 4 to the 3/2 is 8 minus 0. No, 8 minus 0, which is 32 over 3. Final answer. Okay, so that one's a bit annoying. It requires a bit of tricky visualization, but once you have the visualization, you are mostly fine. I'm going to go ahead and plug in this computer now real quick because it's actually messing with how my note-taking app performs. So let's get this. Give me 1 second. All right. Now this should get a bit better. Ooh, okay, that's better. Okay, and now number 7. These integrals give the area of a region in the xy plane. We want to sketch the region, label the bounding curves, and give the corresponding points where the curves intersect. Okay, so there's 2 parts. We're going to start with x going from 0 to 2. So x starts here and ends here. or between these two curves. And then y goes from 0 to x squared minus 4, which is this region. It's like a parabola. Oh, wait, no, x squared minus 4, which is this region. And so this is the first part of the region. I know it intersects here because if I plug in x equals 2 into x squared minus 4, I get y equals 0. Okay. Now the other region, I'm going to draw this separately, and then I'll combine them at the end. X can be between 0 and 4, so it goes further out. And then y can be between 0 and root x. Okay, so let's see. Root x is this function. X can be between 0 and 4. And then y can be between 0 and root x, so that is this region right here. And if I want to combine these two, then let's see, this becomes, I'm going to say it's, I have root x there, and x squared minus 4 here, and it is this region. Okay. That's not quite right, is it? It's this region, which is a really weird region. I don't know why they would give this, and it makes me worried that I set something up wrong. But I don't see any mistake I could have made, so I'm just gonna assume that this is right. Okay. And it's not looking to me like changing the bounds of integration is going to make these integrals or the bounds any nicer. And so we'll just keep it like that. What else did it ask us to do? Label them with their equations. So this is y equals root x, y equals x squared minus 4. This one is x is equal to 4. And then that one there, the horizontal line right there, or I guess, no, not that horizontal line. This horizontal line from here to here is y equals 0. And x on that curve specifically is between 2 and 4. Okay. So now we want to find the area of this region, and I'm just going to do this by doing this integral directly. So this first one, integral from 0 to 2 of, let's see, that's just 4 minus x squared dx plus integral from 0 to 4 of root x dx. Okay, so that is 4 times 2 minus 1/3 times 2 cubed plus, okay, then I can't do this other integral in my head. That is 2/3 x to the 3/2. This is 8 minus 8/3 plus, let's see, 4 to the 3/2 is 8, so that's 16/3. And so our final answer is 8 plus 8/3. Okay. So that's that problem. A little, oh, I need to label the vertices. Okay. This one is, let's see, x is 4, and so y is 2, plugging into that equation. Here, x is 4, y is 0. Here, x is 0, y is -4. Here, this one is at 0, 0, although I don't know how useful that is. And then this vertex here, this last one, is at, what, 2, 0? No, where was it over here? Yeah, 2, 0. Okay. Great, and so that's that problem. That one's a bit annoying. It's a bit weird. It's a very weird region. But we found the area of it, which is really cool. Okay, that's that worksheet. A few hard problems, a few important problems. As always, let me know if you have any questions, and that is it.